Hi, I'm Olga. I work for Microsoft. Today, I would like to present our work on shared online event trend aggregation. In order to derive reliable, actionable insights about the stream, we must consider each event in the context of other events of the stream. We will not derive reliable insights by looking at single event in isolation. In algorithmic trading use case, a single event corresponds to a single stock value. It could be part of an uptrend, a downtrend, or an outlier. Even an event sequence of fixed length could be just a local fluctuation. Only an event trend, which corresponds to an event sequence of any length, can derive reliable insights. In fact, the longer an event trend, the more reliable it is considered by algorithmic trading systems. Event trends are everywhere. For example, a path of an infection spread, a trajectory of a shared ride, a circular check kite, or an increasing load of a system component. In the worst case, the number of event trends grows exponentially with the number of matched events. In order to deal with this complexity, streaming applications run event trend aggregation queries to derive more summarized and abstract insights about the stream. For example, this query computes the number and duration of trips in which the driver drove to a pickup location but did not pick up the rider. A streaming application executes a workload of such event trend aggregation queries over a high-rate event stream. In this work, we aim to minimize the average query latency of all queries in the workload. This problem turns out to be rather challenging. First of all, we need to enable real-time response despite exponential complexity. Second, we need to trade off between benefit and overhead of sharing. Lastly, we need to enable lightweight sharing decisions over bursty event streams. State-of-the-art approaches fail to address all these challenges. Some of them do not support Kleene closure, therefore they cannot express event trends. Some of them do not define online aggregation, therefore they do not enable real-time execution. Usually their sharing decisions are static, therefore they miss sharing opportunities at runtime. Our Hamlet approach compactly encodes all event trends in the graph and propagates the event trend aggregates along the edges of the graph. In this way, the actual event trends are never constructed, and we reduce the time complexity from exponential to quadratic. We define sharing benefit model and monitor sharing benefit at runtime. Based on the sharing benefit, we make decisions to split and merge graphlets at runtime. Assume query Q1 detects event trends which consist of a single request event followed by one or many travel events, and assume two requests and one travel event arrives. Two event trends are detected. These event trends are represented by edges which connect adjacent events in an event trend. While we construct the graph, we also propagate the aggregates along the edges of the graph. An event trend count corresponds to the sum of event trend counts of previous events. As events arrive, we continue constructing the graph and propagating the event trend counts along the edges of the graph. The actual event trends are never constructed, and the time complexity is reduced from exponential to quadratic. However, there can be multiple queries in the workload, and therefore there will be some recomputation overhead, which is highlighted in red in this equation. In order to avoid this recomputation overhead, we partition the graph into smaller graphlets and share some of these graphlets. Shared graphlets are highlighted by gray background. We draw the edges between events the same way we did before. However, now this is complicated by the fact that the set of predecessor events can be different for different queries due to different patterns at different predicates. We address both challenges by introducing snapshots. A snapshot is a variable, the value of which can be different per query, and we store the value of snapshots per query in a table. We propagate these snapshots along the edges of the graph the same way we did before with constants. But of course, this snapshot maintenance introduces certain overhead, which is highlighted in red in this equation. We trade off between the benefit and the overhead of sharing at runtime and make dynamic sharing decisions. Due to this flexibility, Hamlet outperforms state-of-the-art approaches by several orders of magnitude. In practice, this means that Hamlet terminates in milliseconds, enabling real-time response of streaming applications.